So I'd like to introduce our presenter. Today we have Joe Boaler. Dr. Joe Boaler is a professor of mathematics education at Stanford University and the co-founder of UCubed. She's an analyst for PISA testing in the OECD and author of the first MOOC on mathematics teaching and learning. Former roles have included being the Marie Curie Professor of Mathematics Education for Europe, a mathematics teacher in London Comprehensive Schools, and a researcher at King's College in London. Now, I'd like to turn it over to Joe.
Good morning, everybody. It's really great to be talking with you all this morning. I know we have people from across the education sector and from many different countries, so welcome. Whether you're here within the United States or in a different country. It's always great to have the international participation. So I'm going to be sharing some research today, some of which may be new to you and some of which is probably less so. And we're going to watch some videos together also. And I'll just jump straight in by telling you that I was in Norway yesterday. Seems amazing. But it was a really interesting event. I thought you'd like to hear a little bit about it. In Norway, they present a mathematics prize. It's called the Abel Prize for Mathematics. And it was won by a mathematician called Yves Meyer. And what's really nice is they also have a teacher prize that goes along with it. And so I thought you'd like to see some of my photos from Norway. The first one, this is the Yves Meyer being presented with the prize by the King of Norway. That was pretty exciting. And this, I just thought you'd like to see a picture of this is where the king lives. And those banners are actually for the prize, the mathematics prize, which there is a whole series of events week-long in Norway around this mathematics prize. So it's pretty exciting, great that they highlight maths in that way. This is the teacher, Hanan Mohammed Abdelrahman, who won the teacher prize. And without any of us knowing this, what was amazing was when she was presenting to everybody, she was showing all the things from UCubed that she uses in her teaching and very strongly talking about how she communicates to students that there's no such thing as a math person and that anybody can learn math. So that was really great to see that and see UCubed getting out far and wide. And this picture I thought you'd like to see is from the banquet. We went to a very fancy banquet the night before last, and lots of mathematicians were there from international group of very important mathematicians. That's a picture of me with the award winner. And then one of my favorite moments of the evening was the chat with the Minister of Education for Norway. Here he is with myself and Kathy Williams from UCubed wearing his national costume, which I loved. He said to me, "Do you think your American colleagues will think I'm from Lord of the Rings?" So I don't know. I don't know what your answer to that is. But anyway, that was a great conversation about 21st century mathematics in Norway. So starting some of the things I want to share with you today, I am working more closely these days, really at the intersection of mathematics and learning about mathematics and also neuroscience. And we're doing that partly to dispel some really important myths that are out there about maths, and in dispelling those myths, we find it changes people's relationships with maths pretty profoundly. So it'd be no surprise to anyone that I'm going to start with this idea that we know now that nobody's born with a maths brain and nobody's born without one. And in fact, incredible research on brain science, brain plasticity, showing that everybody's brain can grow and change to learn any mathematics. And we need to get rid of the idea that some students are born with a maths brain and some are not. So the next slide was animated, but it's not going to show up as an animation in WebEx, unfortunately. But oh, not this one. So the brain, we know, is our most complex organ. It's made of over 100 billion neurons and several thousand connections between them. And how do we grow a maths brain? How does it happen? This is the slide that's no longer animated, but what it would have shown you is that when you learn something new, there's one of three things that happen. One is a new brain pathway can form. Another thing that can happen is a current brain pathway that you already have becomes strengthened. And then the third possibility is that brain pathways that you have connect with each other. So when we think about students having a mathematics brain, this is how you get one, from learning new ideas that form pathways in the brain and then stay with you for you to use in your brain from that point onwards. And that seems pretty important for students to know, that that's how brains form and learn new mathematics and new mathematics pathways. And that's really what's meant by growing your brain. Some of you will know that we've been sending out messages that mistakes grow your brain, and mistakes are really good for your brains. And that's what really that sort of brain growth really means. Sometimes it's forming pathways, sometimes it's strengthening and pathways and making connections between them. So really interesting new research coming out, I think, on brain connections. So people wonder what makes people more intelligent and know more things and more accomplished, and they really try and figure out what is it about their brains. Some people think you have to have got a larger brain. It's not that at all. And in fact, what makes people more accomplished, more knowledgeable, is a stronger set of connections between parts of the brain, as it says here, the dynamic interplay of neural networks that operate in concert and draw from different parts of the brain at once. So today I'm going to talk to you about how we encourage those brain connections. There was a really interesting article that recently came out in National Geographic, and it was called What Makes a Genius? They were trying to figure out if we call certain people in the world a genius who have just done amazing things. So they talked about Einstein and Michelangelo. What makes them different in their brains? And they actually have Einstein's brain in a museum chopped up, and people stare at it all the time. There's no difference in size of brain, but what they're doing now is bringing in people who are super accomplished and having scans of their brains to look at what's going on inside their brains, and they find, as it says here, that there's quite a notable difference between those that they think of as a genius, that there is more communication going on between the different hemispheres. Those people are more flexible in their thought processes, and more contributions are coming from different parts of the brain. So clearly this is what we want to develop in kids, more communication between parts of the brain, more connections. And mathematics can play a really important role in that. So lots and lots of evidence that people may be born with differences in their brains, but those differences are really eclipsed by the millions of opportunities to grow and change brains. And all students have the potential to learn any level of mathematics with the right teaching. So I want to have us now look into something we did at Stanford recently, and that is we brought 81 students onto campus. And we gave them these different messages about brain science. We told them that mistakes are really important and struggle is really important. We told them that speed is not important. And then we taught mathematics differently as an open creative subject that really backs up those messages we gave them. And the new online class that I have coming out in the summer is actually based around the videos that we took of camp. Everything was filmed by a filmmaker, and we're going to watch some of that today. This site's a little mushed together. We've lost some of it, so we'll send this out to you after the webinar. But we asked, what would happen if we changed all of these things? We stopped kids thinking that you're a maths person or you're not, and we replaced an emphasis on speed and procedures with one on depth and creativity, and we got rid of the idea that there's one way and instead celebrated the multiple different ideas students have and different ways of visualizing, and what's lost at the bottom is really moving away from work just being individual to being a collaborative process. So this graph shows you the pre-scores of the 81 students we brought to campus. It was a test they'd taken in their district on algebra, and what you may be able to see there is 81 bars that represent the 81 students, and you can probably tell there was a wide range of achievement amongst the students. We had very high achieving students, we had students who'd scored 0 on the pre-test. We put them into 4 classes, they were all mixed, we didn't have any tracking or grouping. And then we taught them open creative mathematics for 18 lessons. They were with us in the mornings for the lessons, maths lessons. I was a teacher, Kathy and others, and regular classroom teachers also. We had 4 classes. And then in the afternoon, they were able to sort of run around campus with my undergrads. So they had this day's experience on maths. And at the end of the 18 lessons, we gave them the same district algebra test that they'd taken in their district. And even though we didn't focus on that test at all, the scores of the students, as you can see, it massively went up by an average of 50% per student, which is a huge amount for an educational intervention. Not all students, as you can see, increased, but the increases you'll probably notice come from across the achievement spectrum: high achievers, middle achievers, low achievers. And that difference is equivalent to 1.6 years of school, so pretty huge. These are our kids on one of the last days of camp, wearing our UCube t-shirts, making our UCube logo, doing a pretty good job. And I thought we could, first hear from just one of the students reflecting on their camp experience. They said this: they taught us how math is for everybody, and I believed that I wasn't a math person before, but now I believe that anybody can do math, and that helped me a lot. And the way I thought that math was all about right answers and wrong, but it's really about ideas, and it's very creative, and that helped me like it a lot more. So I chose this because it has two things in it. One was we changed the students' beliefs about who they were. All 81 of the students on the first day told the researchers, "I'm not a math person." Didn't matter if they were low or high achieving. They could name the one person in their school or their class that they thought of as a math person, the one who put their hand up really quickly. So we changed that idea for them. We told them there's no such thing as a math person. Everybody can do mathematics and grow brains. And then we also, as the student said, we changed maths for them. So they didn't see it as a subject as right and wrong answers, but one about ideas that's very creative. So we're going to watch now a little film that a filmmaker made. And what I like about this film is, so she filmed our teaching, but she also filmed the students in school and did a little sort of what happened before and after the camp that we can watch now.
Some people think I'm not good at math. I can never do anything. I'm not good at it. I'm just going to give up.
A lot of people think of it as like prison, like you don't have any freedom.
Okay, time to go to your notebook. Okay, read chapter 1. Okay, here's your worksheet.
The math textbook, it's kind of like the Bible. You have to kind of worship the textbook, and I don't really like that.
Everybody's going so quickly, and I thought if I didn't go quick, people think I'm like not smart.
I made a lot of mistakes, and I got really sad about it.
You make a mistake, you're pretty much done. Yeah.
They can't do it fast, and they're so smart because they can, and I'm not smart, and I just kind of stopped.
You feel like you're serving a sentence for like nothing.
I love it. That does look like a cuboid.
Oh, we got it!
I've done better with math when I was talking with people, sharing ideas.
4 or 5 brains work better than one.
I'll see it one way, but then someone else will see it another way, and I'll be like, oh my gosh, that makes so much sense.
I love that we're getting different answers out, because lots of problems in math, there are different answers.
Have more than one way to solve the question. Because in real life, you're not gonna just do one thing. You're gonna do many things. You're gonna need to use different methods. Yay!
No, hold on. Take your time and just experiment with every way that could possibly work.
You definitely have to be patient because certain problems, they take forever.
Math isn't about speed, and you can make mistakes and you learn from them.
Yeah, I did that too!
Yes!
Told you!
Math isn't like the enemy, and it can't hurt me.
You can run wild, you can pass ideas by each other.
I thought that math was all about right answers and wrong. Now that I believe that math is really about ideas and creativity, it's a lot more inspiring.
I hope you liked watching that film. It's great to see the kids. And that is on our website under videos if you'd like to show other people or share it with others. So some of the different messages we gave the students in camp were these, and we know these messages had a big impact on them. We told them that mistakes and struggle and challenge are really important for your brains. There are times when your brains are growing the most. We told them that talking about math is really important, and it has a special name in mathematics, which is called reasoning. That's what makes somebody a mathematician, actually. Scientists prove things by finding new cases or counterexamples, but mathematicians prove things by reasoning, by making logical steps between ideas. And we told our students it was really important to reason with each other. We also told them that in mathematics, people, when they have sort of ideas that are half-formed ideas, they call them conjectures, a bit like a theory in science. But in mathematics, they're called conjectures, and we learned to talk to each other about different conjectures we had. And then we also told students, and this is really the topic of today, that when we visualize and see mathematics visually, and when we think about numbers, those involve different parts of the brain. When we think about mathematics as a set of words, that's another different part of the brain. And when we think about those things together, when we see something visually and we think about it numerically, that causes a brain connection to happen that's really important. So we wanted to start the camp by really being very clear that we want to see maths visually, and maths is a really creative subject where we get to see it in different ways. And that partly came from this research that I'm working now with the neuroscientists, and what they now know is that when people work on something mathematically, there are 5 different areas of the brain involved. And 2 of the areas are visual pathways. And in fact, the dorsal visual pathway is the main brain region for representing quantity. So when you improve your mathematics understanding, it's not about just building up knowledge in one area, but it's about communication between different areas of the brain. When mathematics for students is just always about numbers, that's really strengthening one part of the brain and not encouraging those connections that can come about when it's also visual or about words. So these are the 2 visual pathways that you see in this picture, and what we want is connections to happen between these different mathematical pathways. And when we use numbers but also visuals and words and algorithms, and we communicate between these different ways of knowing maths, that brings about those really important brain connections that we see as part of the Genius study. This was one study at Stanford where they studied students between the ages of 8 and 12, and they found that as they got older and learn more, their brain becomes more interactive, and that the connections develop between symbolic and visual representations of number. Those are particularly important connections. So we've written more about this if you'd like to read about it. We have a paper on our website that's called Seeing as Understanding, with different ideas. And I often say to teachers, it's really good to make all maths visual, but some teachers haven't themselves had experience of maths as a visual subject. And so if that seems difficult, like how do I make this particular idea visual? I think the best advice is ask the students. They're really good at coming up with different visual ways of expressing maths, and that's always a great thing to do. So I thought I wanted to show you one of the first activities I did with the students in camp. This is a 6-minute video we're going to watch together. And it's called a visual dot card. I know some of you know about dot cards, and we did this really early on in camp, partly because I wanted students to see that maths was a subject that people see in different ways. There are many different ways of seeing it. I also wanted them to know that maths is a creative subject, and that we value the different creative ways that people see mathematics. And you'll see in this video, I think, some of the connecting between numbers and visuals that help those brain connections. So I'm going to move to that video now for you to watch. After the video, I'm going to ask you to think about, why was this an important exercise for students? What was important about it, do you think, for them? Was we now know that when you think about numbers as looking like numbers like this, one pathway in your brain lights up. And when you think about numbers visually, like if I were to draw a picture of a number, a different brain pathway lights up. So when you have different brain pathways light up, it's great. You have like double the impact. So we're going to be doing some connections between visuals and numbers now. So this is what I'm going to do. This is kind of an unusual activity. I'm going to show you up here a collection of dots. And I'm going to show you just for a few seconds. And the reason I'm going to hold it up just for a few seconds is I don't want you to count the dots. So I want you to look at the collection of dots and work out how many dots there are without counting. Is everybody ready? Everybody looking this way? All right. How many dots were there? Let's just all say, everybody.
7.
7. Excellent. So now what I'd like to know is how you see the 7 dots. And why don't we start with Michael? How did you see them, Michael?
So like, I don't know why, but as soon as I saw them, I just started thinking of Star Wars because they look like a TIE fighter. And I know that TIE fighters, like the wings have three edges and 3 points. And then the middle one's also a point.
So, I don't know this. So are these the points? The 3 edges?
Yeah.
So it's this and this and this?
Yeah, that's good.
That's cool. So Michael, I'm going to say you saw it kind of like that. And if we connected numbers to that, we would probably say this was 3 plus 1 plus 3. Great. Who saw it differently to Michael? Maya?
When I saw it, I thought of it more like in layers, like it's more like a circle.
Okay.
With a dot in the middle.
Okay.
So like 2.
So.
And then 2, and then 2 farther apart, and then 2.
Okay.
And then dot.
So. 2.
Yeah.
2.
Yeah.
And 2.
Yeah, and then dot in the middle.
So is it Maya, Maya?
Yeah.
So now I forgot which 2 it was. 2.
Yeah.
2.
Yes.
2.
Yes.
Okay. So I'm going to say Maya's was 2, 2, a dot in the middle, and then that's not a very good dot. These 2.
Yeah.
Great. So what would be the numbers we put with that?
2.
Yeah.
Plus 2 plus 2 plus 1.
Great. Who saw it differently to that? Yeah. Is it Carlos? No. Matt.
I saw it more as like a dice, like if you roll a 5 on a dice. And that with 2 extra ones on each side.
Okay. So the dice you saw was like that, the 5 on a dice.
Yeah. And I just saw 2 extra dots.
And then you saw 2 here?
Yeah.
Great. What numbers would we put with that?
5 plus 2.
Great. Who saw it differently to that? Yeah, why don't we go, Kathleen?
I saw a pattern of 2, 3, and 2 here.
Okay. Say again. Was it 2, 3, and 2? So I'm going to say Kathleen saw it like that. And what the numbers to go with that would be?
2 plus 3 plus 2.
All right.
It's like a baseball diamond is basically a diamond.
Okay.
And then the bases are each point on the diamond.
Would it be this diamond?
So.
Do you want to come out to show me? Probably everyone else knows what you're talking about.
So that's a baseball diamond.
Okay.
Like that.
Yeah.
Like that. And then so from here to here to here to here, that was the first baseball diamond. And then from here to here to here to here to here is
It's
the
another
second.
one. Great. So 2 diamonds. So I realise I forgot to do numbers for second year. We'll come back to that. What numbers would you have, Jack? How do you think you saw it?
I did, and it went kind of 4 plus 3.
Mm-hmm. Because you'd used one already.
Yeah.
Well, you guys did amazingly well. How many different ways of seeing it did we come up with?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Wow. Wow. So, oh, and there's two over here. Yeah. This is one of the reasons we do this, that I wanted to show you this, is people think of math as a subject where there's sort of one answer, one way of getting it, one way of seeing it. And actually, you can solve any math problem in different ways, and people see math differently. So I just showed you a collection of 7 dots, and you saw it in 13 different ways. So now I would like you to write down. Now I'd like you to write down, if you would, and we hopefully can look at some of your responses. Why do you think this is an important activity for students to do? I'm just going to pause a little to let you to think about that and write something down for us. Why do you think this is important? So thank you for those of you who wrote down things. Wonderful answers being given, and I think you can go back and see those after the webinar. I wanted to add one that I didn't think would probably come up, which is we know also from brain science that an important part of the brain is called the ANS, the approximate number system, and it actually develops from students and being able to approximate numbers from collections of dots and other collections of numbers. And it turns out that students with a well-developed approximate number system, that predicts their maths achievement for a long time ahead. So giving students the opportunity to develop that sort of area of the brain where they are able to approximate is just inherently valuable, as well as all the lovely things people are writing about valuing their different ways of seeing and pathways and so on. And to me, I often say to my students, and we do maths together at Stanford, that one of the most beautiful aspects of mathematics for me is the multiple different ideas people have, the way they see it differently, and the different pathways that can be taken through every problem. That is just a lovely thing to celebrate, and whenever my students just come up with a different representation or a different way of showing something mathematically, I always talk about that, that's really such a nice thing about mathematics that many students don't get to appreciate going through school, unfortunately. Oh, this is just a picture I thought you'd like to see of when we did that dot card with a group of teachers in Canada. And you can see there many different representations, some different ones that they came up with. The room came up with, I don't remember, like 30 different ways of seeing it. So a couple of other things I want to share with you before we finish for questions, and that is I've recently come to this scientist who's really interesting. His name is Robert Bjork, and he talks about how when you learn something new, your brain kind of relates it to what you already know. It's very clever about the way it connects things together. And he also talks about how when you retrieve something and when you talk about something, or when somebody's asking you a question and you have to think back in your mind and retrieve it, that itself is an act of learning. And after you retrieve something, that knowledge in your brain becomes more retrievable in the future. So it's really an example of how important it is to have students ask students questions so they have that act of retrieval. And he talks as well, again, on this brain connection piece about the importance of varying examples and situations. So how do you encourage these brain connections and growth? We can probably all agree that a lecture, sitting listening to a lecture, some people can be making some connections, but the opportunities are pretty minimal to make those really important brain connections. Project-based learning has lots of opportunities for that, where students design and collaborate and connect. But for many people, that's a harder shift to go entirely to project-based learning. And what I wanted to highlight is there are many things you can do in between. So I just show you a couple of them that's, not lecturing all the time and maybe not completely project-based, but it's more interactive, more opportunities for connections. And I wanted to go back to what Bjork said, that retrieving information is an act of learning. So some people might think, well, when we give students tests, then that is an act of retrieval. But actually, it doesn't help students as much when it's through a test as when it's in a learning situation, and the act of performing can actually reduce that. And John Hattie is an Australian researcher who looks at effect sizes, and I thought this was really interesting, where they look at how, if you did this, how much impact does it have on achievement. And I thought these two were interesting differences. Teachers who encourage students on tests, the impact of that is so low and weak, it's not even in the desirable range, but engaging people in classroom discussions has a very high impact on achievement. And that's a great way to get this retrieval going, asking questions, having people talk to each other. some cool things going on at Stanford around this. Carl Wyman is a Nobel Prize-winning physicist, and he himself says he hardly learned anything from listening to someone, and so wanted to look at how can you make people's learning more active, even in a big lecture theatre. And what they're doing now at Stanford, he taught the whole physics department here, which is instead of the lecturer talking about things, the lecturer now asks a question of the students, and they talk about it together in groups, and then they vote on an answer together on an electric sort of voting system, and then the lecturer or professor is able to look at the student's answer before giving a sort of mini lecture on the ideas. And when they tried that in physics in university, the achievement was twice as high for people who were asked those questions that they discussed than when they were just listening. So we can all do this with maths. We can all take ideas and open them up and think about how do those methods work, how are they connected to others. Can you represent an idea in a different way, as a picture, as a cartoon, even a doodle? However you're representing an idea differently will cause those brain connections. So I had a few examples, and then I think I'll stop for questions. But math facts are a perfect example. The worst thing we can do with them is blindly memorize them, where it's an active memorization. Instead, we can have students engage with the numbers visually and with numbers, and our activity on our website, How Close to 100, is a perfect example of that. Algebra, if you haven't seen me, I know many of you have, probably showing algebra visually. I have 2 TED Talks, TEDx talks when I do that, so you can look at that. Any algebra example you can make visual in really cool ways. Even things like this, conversion of Celsius to Fahrenheit, it's usually given as rules to students, do this to the number to get this number, and then they practice. Even that we can completely transform by showing it as a visual pattern and asking students different kinds of questions. And all of these questions you see here, engaging with square roots or Pythagoras or can be engaged with visually when we think of different ways to visually represent those ideas, and it gives students different opportunities and helps with those brain connections. I like this example from my friend Kathy Humphreys. Instead of asking students calculate 1 divided by 2/3, which is a calculation in one part of the brain, she totally opens up that question by saying to the students, you may know a rule for working this out, but I don't care about the rule today. What I want is you to be able to make sense of this answer and show your thinking visually. And in a book I have with Kathy, there's a video of the students coming up with these different visual solutions, and it really shifts the understanding of different students. So any mathematics at all can be made visual. I challenge anybody to show me an area of maths that can't be visual. And as I said, ask your students to think of visuals if you don't know ways. And my colleague Kathy Humphreys is often showing the really cool way of making this diamond paper where you fold paper up. And we see teachers using this now where they ask a question, but then the question, like 1 divided by 2/3, for example, has different requests, like can you solve it numerically, can you solve it visually, can you write a story about it? I had an interaction actually with my own daughter's teacher when she was in 4th grade that I thought you'd find interesting, where she was at a school where they had, I don't think homework's ever a good idea, but they had much better homeworks where they did puzzles and kenkens. But occasionally she'd come home with like a list of 40 questions or 20 questions, and parents know that those are kind of the times where a kid's spirits sink, when they're at home in the evening and they have lots of questions to go through. And one time I actually wrote a little note to the teacher. I don't normally do this with my children's teachers. You're probably thinking how terrible it would be if I was your child's teacher. But she came home with a list of, I think, about 40 questions, and I saw her just feel terrible about it. And I wrote a note to the teacher where I said, I asked my daughter to do the first few of these. But then I asked her not to finish the worksheet because I didn't want her to think this is what math is. So it was good. We had a good conversation. But what the teacher changed, and I love this, totally amazing, is instead of giving 40 questions, now she gives 4 questions. But she asked the students, can you write a story about this? Can you draw a picture? Can you do the calculation as well? But can you also do those things? And you can see a little example in the diamond paper there. And that's amazing. that is what will get those different connections going and doesn't make kids feel terrible in the evenings, but they actually feel engaged with math. So a lot of people think practice is very important, but it is important. Practice is what changes that delicate brain pathway into a more permanent brain pathway. But what is productive practice is not repeating the same idea over and over again. It's seeing an idea in different ways, different forms, different representations. So I will skip these and tell you, if you want some lovely visual creative math lessons every year, we give away a free week. It's called our Week of Inspirational Maths. There's already 2 weeks, so 10 days of it on the website. And a new set is coming out of visual creative math lessons that really gives students these opportunities. And those are all planned out for teachers to just take and use off our website. And we're also working on a new set of books, and fourth grade books are coming out this summer, where we've taken the whole grade level and thought about how do we show this idea through big ideas and through visualizing. So those, look out for those. YouTube is going great. We now get 3 million on the site in our months where we give things away, like our Week of Maths, so that's amazing. Our newsletter is open in over 120 countries, so it's very cool. So I think I'll stop now and answer some of the questions that have come in, because I have quite a few in front of me, and if you want to ask a question, now would be a good time to ask it. So I'm going to start off with the first question that actually popped up during the webinar, where somebody said, but surely some people can perform calculations more quickly and more easily. And I think this person was sort of challenging the idea that there's nobody who's just a math person. And it's true. Some people can do calculations more quickly or more easily, but what we know is that has come about because of the millions of opportunities they've had for brain growth and the messages they've been given. So when you see students who find maths more easily than other students, I don't think what you think from that is, oh, this person's more of a maths person. But this person has had more opportunities for that to develop, and we can make those opportunities more equitably available. Somebody said we're doing a summer camp in Chicago, and we've got students for 10 days and 3 hours a day. Is that enough to develop growth mindsets? And yes, definitely. We had students for a longer time than that, it's true. But we recently did a one-day intervention with students where we brought girls onto campus and did like a little mini camp for a day. And even that day, the students will tell you really changed the way they thought about maths and themselves. So definitely that's enough time, I think. Somebody said, how often do you recommend a routine like dot cards for grades 3 to 5? I think it's really good to use number talks of different types every day. So a dot card is a particular type of number talk that's visual, and I love them. And we have them inside our Week of Inspirational Maths, and Sherry Parrish has a book of many different dot cards. But some of them can be numbers as well, and number talks are also wonderful, and you can find lots of information on number talks. And so a dot card or a number talk every day is a great routine for that. Somebody says, I'd love to access this video of the dot card for PD for aspiring teachers. Is it available? So that video is inside the online class, and that's the way that you can get that. So I really recommend for those teachers that you'd like to learn from it, getting them to register for the class would be the best way to see that. So somebody said, once a sense of quantity is developed, is there a point in which efficiency, calculation processes, pathways, etc. should take over? So it is true that after you've really understood something and after you've engaged with it in different ways, visually and numerically, you may get to a routine where you're able to very quickly come up with different ideas or calculation or math facts, for example. Some people think that I'm saying math facts aren't important. That's not what I'm saying, but I'm saying we can learn math facts visually and deeply. And after you've done that, then they are more accessible to use in a more efficient way. And yes, that's fine. But what I try and get away from is a misconception that we do this in the early years and with younger children so that later people don't need this. And that isn't the case. And people need to be engaging visually and with numbers all the time, whether they're 16 or 25. Some people think, oh, well, some people are visual people and they're visual learners, and some people aren't visual learners. That's also a damaging idea, because if you don't think visually, or your students don't think visually, you need visual learning more than anybody to develop those pathways, and it's not okay to just think, oh, well, we'll just work with numbers with those people. We want everybody to be developing those and using those pathways through their lives, not just in some years. Somebody said, what are your thoughts on how calculators fit into student problem solving for our middle grade students? I always think the calculator question is never a question of do you or don't you. I mean, yes, we always want to use really good technology. We may not have students use calculators all the time, and we don't want it as a replacement for number sense. Number sense is really important for students, but when they get past and into higher level mathematics, or in middle school, for example, it may be better to have them use a calculator sometimes, so you can get on to other ideas that you're working with them on, so they don't have to be calculating everything, and that slows everything down. And that's fine. Yeah, you want to develop their number sense, but yeah, at times having a calculator is a really good thing. It allows you to move into other content, which is great. Our 6th to 8th grade uses CMP3 curriculum. Does this curriculum still fit the bill? In my mind, so yeah, I think the CMP curriculum is one of the good curricula that are out there. I don't think any published curriculum at the moment pays enough attention or has taken it on, the brain science and the knowledge we have that we need to think visually and creatively. So that's why we're actually working on our own set of materials now, but definitely that's one of the better ones to use. When are the new curriculum books released and how can we get them? So the grade 4 book is on Amazon now. The grade 5 will be the one that follows it fairly soon afterwards. And then I believe 3, and then we're moving to middle school grades, and then K to 3. But it will take us a while. We're a little tiny team at UCubed, and we're really trying to make really high quality materials for people. So somebody said, how do you keep the spirit in practice? Parents and students get frustrated with, instead of talking about problems in multiple ways, they are tasked with memorizing algorithms. It's the same old way. I'm not sure what that end bit means, but so I don't think we ever need to have kids just practice numerically without visuals, without different ways of thinking about it and different ways of doing it. The most successful students are the ones who understand algorithms, not just reproduce them. I did a big analysis with the PISA team, which was really interesting. We had data from 13 million students from across the world, 15-year-olds, and we were able to analyze their approach to mathematics. Some of the students had memorized their way and thought memorization was the way to be successful, as many people have in the US. Other students were seeing big ideas and seeing connections. What we found by analyzing this data set was the memorizers were the lowest achieving students in the world. They were the lowest achieving students within each country, and every country that had a high number of memorizers was a low achieving country. The US is one of those. So that, we wrote it up in an article for Scientific American, and you can find that on our website. So I think we're coming up to 11 o'clock. Did you want to finish some things off for us?
Thank you all again for joining us today with the webinar. Have a great day.